Hello again. For us, this is the start of Lecture 8. This is typically after our first exam in the Changle Bowles text. That means we're going to start on the Chapter 4. For me, when I think about these chapters, I think about Chapter 4 is basically First Law for closed systems, and Chapter 5 then is First Law for control volumes. And for us, I normally group those two chapters together into one test, one exam. So that's what we're going to get started on. So again, Chapter 4 focuses on, both these chapters focus on First Law for different kinds of systems. Chapter 4, we're going to focus on First Law for closed stationary systems. So I'm going to switch screens here. First Law. All right, let me stop sharing. First law, in its purest, rawest differential equation form, just simply says that the energy in minus the energy out is equal to the change in the energy for our system with respect to time. E dot in minus E dot out equals dE dt. Now, what we will often do is for a closed system, we are often much less worried about every little differential size slice in time. What we'll normally do is we'll say, well, this is essentially, this is approximately the total change for our system divided by a total change in time. So the rate of energy in minus the rate of energy out is approximately equal to a total change in the energy of our system for a total period of time. And this doesn't necessarily, this assumption wouldn't necessarily have to be limited only to a closed system. In fact, we can do the same thing with control volumes, but this is the assumption we're going to make in this case. I'm going to move delta T over here. So I've got a couple of rates. And if I take these rates and multiply them by an amount of time, so that's E dot in minus E dot out, and multiply them by a period of time, I no longer have rates times time, I get total amounts. So I get the total energy in minus the total energy out, then becomes, so the total energy in minus the total energy out equals the total energy change for my system. And then if I go back and we talked about this in chapter 2, we said, don't, you've got this, there's all these terms here, and be careful trying to memorize a big, long equation. Think about it kind of piece by piece. Think about what are the types of energy that could come into or go out of a system. Well, that's going to be, there's three of those. There's going to be heat, there's going to be work, and there is, if I have mass crossing the boundary, that mass has its own energy. And then I've got all of these terms going out. So add the ins, subtract the outs. So minus the heat out, minus the work out, minus the energy of the mass out. And that's going to equal the change in the energy of my system. This is the energy in, energy out. Now, I just realized I'm going to really need a lot more room to work with here. But we'll remember it's a closed system. Because it's a closed system, there is no mass crossing the boundary. So since there's no mass crossing the boundary, that's only going to leave Q and W, the heat in plus the work in, minus those terms going out, minus heat out, minus work out. And that's going to equal the change in the energy of my system. Well, it's a closed system, so the mass is going to be constant. And there are three types of energy in my system that can change. That is internal, kinetic and potential. So again, I don't recommend you try to memorize this big long equation. Memorize this, right? That's really what you want to memorize is this idea of that in minus out equals change. That's what you want to remember. In minus out equals change. Then you can break that down. Okay, what are the things that can come in? Well, it's heat and work, and if it's a closed system, there's no mass, so that's it. And those things going out, minus those things going out, heat and work going out. That equals the energy that can change. What are the energies that can change? Well, I've got internal, kinetic, and potential. So I need to track the change in all of those energies for my system. Now, we can simplify this a bit further. For a closed, and I'm going to add another adjective here, stationary system. And I would ask my class if you guys are in front of me. All right, what does that mean? What does a stationary system mean? And that, hopefully somebody will say, well, it's not moving, right? Its motion is not changing. So if its motion's not changing, something happens. That means it's moving essentially at the same speed, and it's not changing elevation or distance from the center of the Earth. So if I've got a closed system, there's no mass crossing the boundary. If I've got stationary, that means there's no kinetic or potential energy changes. I'm left with this. Qn plus work in minus Q out minus work out is equal to M delta U. This is the first law for closed stationary systems. This is the most common form of the first law equation we'll use in chapter 4. It's very common. We'll be dealing with a closed stationary system. The other type of system we'll encounter is what we call a steady flow control volume at the beginning of chapter 5. We'll do a similar simplification where we go from this differential equation and we get it all the way down to, because I'm not expecting you to be able to work with differential equations yet, this is the simplified form that you'll want to use for a closed stationary system. Now, those of you that are joining us from other parts of the internet and you're reading your textbook, and maybe you've got a different textbook and maybe a more traditional set of authors, and they might say something like, well, Q minus W equals U. And I guarantee if you went and just looked up on the internet, First Law of Thermodynamics, you're probably going to get something like this. That's okay, because we're making some assumptions to use this equation. That's assuming Qn is positive and work out is positive. What do I mean by that? Well, by the way, this is the one in our text, in the Changle and Bowles text. This is where we're going to start. This is the one we're going to work from. This is how they're going to solve their example problems. This is how I'm normally going to solve my example problems. It's a lot easier, in my opinion, to think about it this way. I was taught this way. I was taught that you add the heat ends and you subtract or you add the work out. You subtract the heat out, and you subtract the work in. And that's what we call a traditional sign convention. And it's based off of this idea that if we were to let a quantity we might call Q net in, the net heat in, that would be the difference between the heat in and the heat out. So if we define this term Q net in, we call that Q in minus Q out. And we define another term, the net work out. The net work out. The net work out would be the difference between work out and work in. Now, if I do that and I take this form of the first law and I kind of massage the equation a little bit mathematically, I can say, well, Q in minus Q out, I've taken Q in minus Q out, and I'm going to subtract from it a quantity of work out minus work in. Notice what I've done here. I've taken this negative sign off of work out. I've taken this positive sign on work in, and I've flipped it to a negative sign. So basically, I've undistributed this negative sign that is here and pretend there's one there and take it off. So I've got work out minus work in times a negative sign, that's minus work out plus work in. So it's the same thing. And I'm going to say that is equal to m delta U. And that is what this is saying. This is what we call the traditional sign convention. Traditional sign convention is a very simple way of writing the first law, where we say, okay, the heat in is positive. Notice here, this one's positive, this one's negative. And the work out is positive, where this has got the positive value and that one's got a negative value, but then the work term carries a negative sign in the first law equation. Um, that's a lot of stuff to remember, and it's not hard. You can remember that if you want to think about it this way, that's okay. And the reason this came about, again, this is kind of what we call the traditional sign convention. The science of thermodynamics was born in a time when we were trying to construct the best steam engine we possibly could. So the steam engine, I was putting heat into it, and I wanted to get work out. So these were the things that I wanted. I wanted to put heat in. I didn't want to lose heat out. So heat out was negative. Heat in is positive. That's what I wanted to do. And I wanted to get work out. So that was the positive quantity. I didn't want to have to put more work in. I'd have to pay for that or put in effort. I wanted to put heat in, that's positive, and I wanted to get work out, that's positive. If I'm just dealing with an engine, that sign convention makes sense. And that's, again, that's how the whole science of thermodynamics was born, trying to get the most we could out of these engines. And that's the reason this version of the first law still prevails today substantially. Now, this presents some other challenges later on. It's a little harder to mess with and deal with a control volume with this. This is a much more generic way. This doesn't have to only be applied to engines. You don't have to remember a bunch of signs. All you have to do with this one is remember in minus out equals change. So I'm going to add my ins, I'm going to subtract my outs, and that's going to equal the energy change. And if it's a closed stationary system, all I've got is heat and work coming in and out, and all I've got is internal energy changing. This works, nothing wrong with this. You got to remember the rules. The other thing to point to here is whenever you see a very simple equation describing somewhat complex phenomena, because again, this equation down here is a simplified version of this differential equation. Whenever you see a simplified, very, very simple equation describing complex phenomena, as an engineer, big red alarm bells need to go off in your head saying, hey, that's a very fancy tool. I need to only use that tool for very specific circumstances. There's rules and laws and assumptions made to make it this simple from the complex differential equation we start with. Make sure you know what those rules before you use this equation. If not, use a version of the equation that you know and understand. This is imperative today in the time where artificial intelligence is becoming so prevalent. It may or may not know all the nuances and it might get some things wrong. You as the engineer, that's how we kill people, is using an equation, not knowing the assumptions or the rules or how that equation got so simple. Something was done to make it that way. So just going to keep that in mind. That's a soapbox you guys will hear me harp on throughout the rest of the course. But it ain't. This is the version of the first law that we will use for closed stationary systems very often. And we'll simplify this down to just the terms that we need for our particular situation. And so that's kind of how this is going to go for the rest of chapter 4 as we progress along. Okay. From there, here's my slide if I want to write on there, simplifications of the first law. Now, there is a term here in your text that in the Changle and Bowles text that they will apply to a piston cylinder if we want to understand or know that that piston cylinder is constant pressure. The pressure in a piston cylinder device can change, right? Piston cylinder, a generic way we would draw it is just we would draw this cross section of a cylinder, and then we'll draw basically a lid to go on top of that. We might draw like some kind of a little stem coming out of that. I've got an actual graphic of one later that's moving up and down. But the idea is that this lid can move up and down. So a piston cylinder is a device where the volume can change. Piston cylinder is a device where the volume can change. The pressure might also change. Pressure might also change. I've definitely seen some texts where they give you a piston cylinder and they want you to assume that the volume does, or I'm sorry, that the pressure doesn't change in your piston, and that's not realistic. Um, if this textbook wants you to assume that the pressure can change, they're going to tell you that it's either they'll tell you it's a constant pressure process. They might occasionally they'll use the term isobaric. That's pretty rare for this particular set of authors. I don't know why they don't use that term, but what they will tell you is kind of a more realistic scenario. They'll say, "Hey, we've applied a constant amount of weight to this piston." That's what they're saying by this weighted term. They're saying, "Hey, we've added a constant amount of weight onto this piston, and that's going to generate a constant pressure as the volume of this thing changes." So that's just something that they will tell you. All right. My alarm went off a little bit ago. I'm going to stop recording here and move to the next video.